So thank you, everybody. This is joint work with Graeme, Gange and Peter Stuckey of the University of Melbourne, and also Peter Moulder from Monash University. And it's sort of a continuation of Mihai's talk. We're also talking about automatic table layout. And why are we interested in automatic table layout? Well, tables are used and provided in pretty much all document processing software. And in most document processing software editing tools, it's really, as Mihai said, really painful to lay out tables to determine the best way of choosing the best column widths, for example. Tables are also widely used in HTML and other web standards. And so what this means is there's at least three reasons why automatic table layout is important. Firstly, because it can make authoring tables easier. Secondly, because it can support automatic adaptation of documents on the web to different viewing devices, and in particular mobile devices. And finally, automatic table layout is really important if you have dynamic content. So, and that's important in variable data printing, for example, but also for other content on the web. So automatic table layout is important, but as Mihai said, the bad news is that it's NP hard. So this was shown by Anderson and Sopti, and the main reason that it's NP hard is if you have text in the tables, then you have different configurations, different choices of text configurations for the cells in the table, and choosing the right combination of text configurations is a good example of combinatorial optimisation problem, because there are trade-offs, global trade-offs between the different choices that you make. So because of this, the majority of approaches to table layout have been heuristics. Most computer scientists are scared by NP hard problems, and they go away and they try and come up with a heuristic. So one class of heuristics, such as the HTML table layout algorithm, is based on basically looking at the content of a column and then using this to guess a column width, so perhaps proportionally based on the content. Another approach is to use iterative column narrowing or widening, and there the idea is that you start out from some for example, some very wide configuration and choose to narrow a column step by step while increasing the height as little as possible. Another class of algorithms are based on the idea of approximating the table content by its area. So generally, all of these heuristic approaches, well, they have polynomial complexity. That's why you're using a heuristic. But of course, because of this, they're not guaranteed to find an optimal solution. So here's a simple example. This was a table laid out with Gecko. It's a fairly uncompact layout. And you can actually do quite a lot better. So this is a much more compact layout, which can be found with other approaches. So what are these other approaches? These are complete approaches. So what we're interested in doing in this talk is exploring complete approaches for table layout. That is, approaches that are guaranteed to find an optimal solution. What do I mean by an optimal solution? Well, we're interested for a particular width in finding a minimal height layout, or most compact layout. Why are we interested in complete approaches? For at least two reasons. The first is as a benchmark for evaluating heuristic approaches for table layout. So how good are your heuristics? Well, the only way to evaluate that is to actually know what the optimal solution is. And that was our original reason for doing this. But also, it may turn out that these complete approaches in practice are fast enough for real-world table layout. Now, of course, any complete approach is going to have, in the worst case, exponential complexity. But as computer scientists, we don't need to be scared anymore, or necessarily scared, by NP hardness, exponential complexity, because in the last decade, combinatorial optimisation algorithms have improved enormously. Okay, so it's now routine to solve hard, large rostering, scheduling applications in other sorts of industries. However, something that we have learnt is that there's no one best technique. So there's mixed integer programming, which Mihai was talking about. There are A-star approaches, there are local search approaches, there are constraint programming approaches. So that naturally leads on to what I'm going to be talking about. Whoop, not quite. Now, with complete approaches, there has been relatively little work on complete approaches. The main work in table layout has been on heuristic approaches. So Wang and Wood, quite a long time ago, talked about a branch and bound approach. Mihai and Pat Healy gave a paper last year about a MIP approach, and Mihai has another, the preceding paper here has extended that. But that's basically the work, previous work on complete approaches to table layout. Now we extend this. Oh, I'm sorry. So in this paper, what we do is to look at other approaches to complete table layout. So we look at 3 new approaches. The first of these is based on A-star. The second is a traditional CP approach, and we also look at a CP approach that uses learning. I'll explain those in a little while. We also do a fairly complete evaluation, and in particular, we look at real-world problems. So something underpinning this paper and the other 2 papers in this session, which I think is really important for everybody to go home and take home as a takeaway message, is that automatic layout really is constrained optimisation, and this is a good way of thinking about it. So why is this? Well, layout requires finding position and size for the document elements. So essentially we have variables which capture those geometric properties. We want a layout which satisfies structural and designer specified geometric constraints or relationships, which are just constraints on the values that those variables can take. And we also want something that will maximise aesthetic quality and readability, and we can encode that in an objective function. So layout is a constrained optimisation problem. So how do we formalise table layout as a constrained optimisation problem? This is very similar to Mihai's formulation before. So what we have is the unknown variables in our problem are the row heights and the column widths. And what we want to do is to minimise the sum of the row heights, the HIs, so that we minimise the overall table height. And we do that with respect to the following constraints. We want to ensure that the table width is less than some set width, so the sum of the column widths has to be less than that. And then for each cell, we have a set of configurations that cell can take, different numbers of lines of text, and we require that for each cell, the width for that cell, so the width of the columns that cell spans, has to be greater than the width of the configuration that we've chosen, and similarly that the height of the cells that cell spans has to be greater than the configuration height. Now, looking at table layout as a constrained optimisation problem, of course the advantage is that suggests that you can use all the many, many, many different techniques that have been developed for constrained optimisation. So, I'll quickly review MIP technologies and how they work in this case. Now, MIP relies, or mixed integer programming, relies on fast incremental solvers that have been developed for solving linear programming problems. So, what's a linear programming problem? The constraints are linear inequality constraints over real numbers, and you have a linear objective function. And a MIP model, a mixed integer programming problem, is a linear programming problem except that some of the variables are required to take integer values. Now, how are MIP problems solved? Well, one of the most common techniques is a branch and bound approach. So how this is done is that the underlying linear solver solves a linear relaxation of the problem, which means that integer variables are treated as if they're over the real numbers. everything's assigned a value, and then if this is not a solution to the original problem, because some of the integer variables have been assigned non-integral values, then the problem is split on that variable. So it's constrained to take the floor or the ceiling greater than the ceiling or smaller than the floor of that value, and it splits two problems. And then these are solved recursively. Now, if the linear relaxation is very close to the original problem, then MIP techniques are very fast. However, they do require complex implementations for very good performance. So in practice, you have to use an off-the-shelf solver like a Cplex, and also the constraints need to be linearized. Now, in table layout, the difficulty, most of the constraints are linear. The difficulty is the requirement that for each cell, the configuration, you choose one of the configurations for that cell. So this has the standard 0, 1 encoding, where you introduce a Boolean variable for each possible configuration for that cell, and then you require that Boolean variable, or it's a 0, 1 variable, you require that only one of those is set to 1 and all of the others are set to 0. Now the problem with this constraint is, yes, it certainly captures the requirement that you choose a configuration for each cell, but it's not a very linear constraint. So we looked at some other methods apart from the MIP technique. The first of these was an A* approach, and the reason for looking at A* is it is certainly one of the most widely used complete search methods for solving combinatorial optimization problems. And it's also a relatively simple technique. So how we encoded table layout using A* is that we had partial layouts, and a partial layout was an assignment of a width for the first I columns, and then you perform a priority-based search through the partial layout. So each partial layout has a penalty P, which is a lower bound on the final table height. And so you keep expanding the partial layouts, choosing the one with the lower bound on the final table height until you reach a layout where you've actually found a value for all of the columns, and then you know, because it's a lower bound, that you've actually found the optimal layout and you don't have to expand and look at any other possibilities. So how do we expand a partial layout? Well, we fix the width of the column. We have to fix the width of the next unfixed column using one of the useful cell configuration widths. Now, where A* approaches, all the trickiness relies in them, is essentially how do you find a lower bound on the penalty function. So what we did was a fairly simplistic idea. You computed a lower bound on each row height in the cell, and for the columns which we've assigned a width, well, of course, the lower bound on the cell height is just given by the cell contents and the configuration in that cell. For the remaining for the remaining columns where we don't yet have a width, well, we just treat that as a single column, which is the width of the unknown part of the table to the desired table width, and then we take all of their content, compute the area of that, and lay that out in that single column. We've also looked at another approach, which is constraint programming. Constraint programming is increasingly used to solve difficult combinatorial optimization problems, and it's basically an extension of backtracking search. So the idea is that you do in table layout, you do a backtracking search through the column widths, but what makes constraint programming effective is the backtracking search is combined with fast finite domain propagation. So this is used to prune the widths that cannot satisfy the constraints. How many people are familiar with constraint programming? Okay, 6. If we look at the simple example here, what we have is a constraint x less than y, strictly less than y, and we have domains for x and y that they must take the values 1, 2 or 3. Now, domain propagation, what that will do, based on the x less than y, will realise that we can reduce the domain of x to just 1 and 2, because there's no way that the value 3 can ever satisfy that constraint, given the values in the domain of y. And similarly, the value y can be taken out or pruned from the domain for y. So what happens is that we combine this pruning domain propagation with the backtracking search as we're going through the trees. Now, the big advantage of constraint programming compared with MIP is that it can handle nonlinear constraints. They can be directly modelled using propagation. And that means that we can directly encode the configuration constraint as an array access or as an element constraint. However, the disadvantage of constraint programming is that it, again, like MIP, it requires complex implementation for good performance, and it doesn't have a good way to direct itself towards the global solution, the global minimisation. It doesn't use relaxation to do this. Instead, it uses a branch and bound approach. So it finds a layout for the table and then tries iteratively to find a layout that reduces the height of that layout and does that until it can't do any better. Another problem with constraint programming is it tends to do the same work over and over again. It tends to revisit similar problems, but it doesn't really learn from its mistakes. So modern SAT solving techniques, that is techniques that have been developed for solving Boolean satisfiability problems, are very good at learning from their mistakes, and they do that using track of no goods. That's assignment to variables which lead to failure. So recently a CP-SAT hybrid approach has been suggested, and the idea here is that you learn no goods when you're doing the CP search. And what that does is basically keep track of, in our context, assignments or column widths which will lead to a layout which is too high. So let's step back a little bit. We've looked at 4 different ways of solving the constraint optimisation problem for table layout. The first of these is MIP, and the advantage of that is that it has a global way. Linear relaxation provides a global way of finding the minimal height solution. We've also looked at A*. Its relative advantage is that it doesn't require you to use sophisticated constraint solving technologies. CP, its advantage is that you don't require, or you can directly handle nonlinear constraints, the configuration constraint. And we've also looked at CP with learning, which has the advantages of CP, but also can learn no goods. So the obvious question is, which is better? So we performed 2 evaluations. The first one, we collected 50,000 non-nested HTML tables from the web and laid those out for 3 fairly reasonable viewport widths. Then we took our A* algorithm and chose the hardest, roughly 2,000 tables from that and viewport configurations. We separated those into columns with spanning cells, so with either column and row spans, which we called the compound tables, or the ones that had no spanning cells, which are the simple tables. We used state-of-the-art MIP and CP solvers. A* was at a bit of a disadvantage. We implemented in a high-level declarative language which made implementation simple but probably slowed it down a little. So what did we find? These are shorter versions of the tables that appear in the paper, but basically what we do is for a particular time we give the number of instances of the tables that could be solved by each technique in that time. So if we look at CP, then in 1/100th of a second we could solve 1,018 instances of the simple table problems. Or if we look at CP with learning, we solved 1,097 in under 1/100th of a second, and we actually managed to solve all instances of the problem, 1,271 of those in under a second. And similarly for the compound cells. So I think what's surprising about this is that all methods were very good, actually. Remember, these were the hard problems. We already took 50,000 tables and found the hard problems out of those. And then pretty much all of these instances could be solved by all of the techniques in less than 10 seconds, and most in less than 1/100th of a second. CP without learning was probably the worst method. And we were really, really surprised by how well A* did. Given the simple implementation, it was pretty competitive with the others. In fact, sometimes performed better. As a second evaluation, we sort of stress tested the methods in a way similar to how Mihai described. So we created bigger and bigger tables. These were quite large artificial tables. And here, look in the paper for more details, but what we found was that CP with learning was actually clearly the best method for these artificial tables. CP without learning was clearly the worst method, and MIP and A* were somewhere in the middle. So, what's the conclusion? Firstly, we've looked at a variety of provably optimal methods for table layout. So previously people had looked at MIP. Well, we've extended that by looking at A*, CP with and without learning, and we found that they're surprisingly effective for real-world table layout. You could actually use them in practice. CP with learning, at least with our experiments, came out as the most robust and scalable method. However, you need to have some skepticism about that result. Firstly, we didn't consider nested table layout. All of the methods could be extended in a way to handle the case that Mihai talked about, where you flatten the table, but more complex nested table layout, it's more difficult to see how to do that. The results, of course, depend on the choice of the evaluation corpus. And finally, and this is probably the most important point, the comparisons depend crucially on the model of the problem that you're using with MIP and with CP, and the choice of heuristic that you're using with A*. So, you know, an obvious question now is that we've seen Mihai's new MIP models is to go back and compare them with these and find out how well they go. Thank you.
Kim, any questions? Kim?
Nathan. Nathan, yeah?
Could you, one thing I'm wondering, use the microphone, thank you.
It's a very simple question. I was just wondering if there's any correlation between the well-performing examples in each of the different methods. So did the fast A* solutions, were they generally also the fast CP solutions?
No, there wasn't. So I guess we got rid of all the simple ones where everything performed well, so we did go back and check them on that. But no, it wasn't necessarily true that this particular table was hard for all of the methods. I'm sure there was some correlation, but it wasn't obvious.
Any other questions? Thinking more about constraint programming experts. Mihai.
I would have asked you this in private anyway, because I'm interested in this topic. Why do you think the A+ has actually behaved so well?
I actually think the table layout's pretty... in reality, it's simpler than you think. It is an NP hard problem, but in reality, you can find a fairly good solution fairly quickly, and that allows you to prune most things away.
Have you found cases, Kim, where the tools just did not find a solution?
Yes, yes. Yeah, for
that
the bigger
would
tables.
go on forever and not
yeah,
find a solution.
none of them found it. That's right.
Thanks.
So if I understood the research goal correctly, you were trying to find truly optimal solutions to, at least initially, to act as benchmarks.
Yes.
And and as you said, in some cases you couldn't, or at least not in a reasonable amount of time. But is there some kind of a lesson for kind of practical problems, or for for real table layout engines for browser development? Or do you know someplace you can take this that goes beyond the creation of benchmarks to improve table layout algorithms that are closer to optimal, and yet you can tell people, we can almost guarantee it'll finish, or we know that if you terminate you'll be close to optimal, something like that?
So, given how fast these algorithms are, I think you could probably use pretty much all of them in a document formatting tool, but maybe have some timeout if it hasn't, or after a period of time, just return the best solution that you've found so far. So it's not necessarily going to be optimal, but it will almost certainly be better than the solutions that are found with existing heuristic techniques. Whether or not that works in a browser, it would depend how much power you've got
Sure.
in your browser.
But it might make a nice paper if you showed that that the results when you terminated that way were good.
We're still good. That's right.
Okay, if there are no more questions,